We discussed quite a few new concepts last time. Let me remind you where we stopped and what we were discussing. We were interested in the systems which allow, in general, we are interested in the system which allows some simplified description of at least certain type of motions. In particular, we started with saying, let's assume that the system can be described in a statistical way, namely that the system is ergodic. That's first important concept which I will repeat. Ergodicity, which simply means that the system occupies with equal probability all allowed places. Namely, if there are no extra integrals of motion, if we have only energy conserved in the system, then the probability we said is the delta function of E minus Hamiltonian of P and Q, dP dQ. And what it means is that it means a statement of tremendous strength, actually, because it tells you that you have, you measure some function of, when we talk about gases, it's about 10 to 23 variables. And we have, they change in a very complicated way because we have some interaction between molecules, they move and so on. And then we say that instead of solving these 10 to the 23 equations of motion, you can, instead of averaging that time average is equal to phase space average. That was the statement we discussed, and then you can identify all the quantities which appear when we perform these averages with what we measure in real life with thermodynamical quantity. In particular, the volume of the phase space, we identified the logarithm of the volume of the phase volume, which we know is conserved when the system moves. So this volume is it's entropy, we said. And actually, there was a subtle and interesting point which we will elaborate a little bit later, namely that in a certain system, the entropy in the system which are of interest, I would say, for statistical description, entropy is growing with time, despite the fact that with the original definition, this original definition with this, I shall not repeat, of course, what I was doing with this integral. We reduced it to the integral of e to the minus beta h instead, the distribution. So it is possible to introduce, instead of energy, talk about temperature. Beta is inverse temperature. That's a relatively easy part. It's just uses the fact that we have many degrees of freedom, and you can calculate this integral, reduce this calculation to the calculation of this integral. And after you do this, maybe I didn't stress it enough, you will obtain the standard, if you the standard first law of thermodynamics, that differential of energy will be temperature minus pressure multiplied, it's probably let's call it omega, the phase space volume. It's a usual volume. And then the whole scheme, after that we embark on the standard scheme of statistical mechanics, which is quite easy and in principle. The difficult part in principle is to understand whether we have ergodicity or not. And I shall only add to what I have said, that we had the coarse-grained picture, and we saw that we can get growth of entropy. Our device can only determine the presence or the absence of the system in a particular cell. And with time, the phase space of our ensemble should become thinner and longer. And that means it's interesting. Well, I will just mention it now, but we will talk about it at the end of the course. It's interesting that this entropy is related to the exponential. For many systems, turns out that the process of thinning and stretching is exponential. And there is the so-called Lyapunov exponent, which measures how fast it expands. It, by the way, obvious that if it stretches, it must get thinner and thinner. So in some system, you can really calculate this e to the gamma t, the factor gamma is. It measures instability in the system to some extent, instability, or it measures sensitivity. Better to say it measures sensitivity to the initial conditions. When you change a little bit the initial conditions, the effect grows exponentially. And I promise you, I will give you at the end a concrete systems where we will be able to detect this. What I'm saying now is that it can be shown that the entropy grows with time linearly, and this Lyapunov exponent characterizes this. There is a complicated a lot of mathematical work. The first time this idea, well, you see, the idea that ergodicity should be related to something like that appeared already in Boltzmann's work. But a real precise mathematical definition of coarse-grained entropy and its relation to this exponential law is what is called Kolmogorov-Sinai entropy. After great Kolmogorov, who was a fantastic mathematician who made a lot of impact on physics. In particular, we will be discussing turbulence, in which he did some basic things. All right, and then that's just an addition, some extra piece of information concerning ergodicity. Generally speaking, it's not a solved problem when you are given some particular dynamical system. It's not really easy, or there's no standard way to determine whether it's ergodic or not. But for some systems, ergodicity and this exponential growth of entropy of the volume of the coarse-grained volume can be proved, and for some in particular, if you have when you have a particle moving on a surface, if you have a particle moving on a sphere, it's of course not statistical. It doesn't have this sensitivity to initial exponential growth. Everything geodesic on a sphere, as we discussed, are just big circles, and if you change a little bit the initial condition, nothing much changes. But if you take a Lobachevsky space, which is a space with negative curvature, it's kind of an analytic continuation to the imaginary radius of a sphere. Then it is possible to prove that the motion is ergodic. It's a compactified Lobachevsky space on which, maybe I shouldn't talk about it now because we will be discussing it later. All right, then we looked at something very simple, some very simple dynamical system in which the goal was to pass from discrete description to continuous description. Turns out, we know it, that in many cases, a very complicated system of molecules can be described. We are not really interested in detailed motion of these molecules. And when we talk about water, for example, flowing in the canal, for the boat on the canal, it doesn't matter how the molecules move. It's some average quantities which matter, average velocity of the flow, and in more complicated cases, vorticity of the flow and so on. So we have to find a way to go from complicated discrete system to a continuous system. And that's kind of, we will describe today the equations of hydrodynamics, which serve to describe this continuous motion. And we do it to pass to it to show how it happens, how come that discrete system becomes continuous, in what sense. I started last time with a simple example, and let me remind you the example, and then we will start. So far I basically was repeating, as usual, the last discussion, adding a few new points here. But now we will approach to the new things which we didn't discuss yet. So we said that if you have a periodic boundary condition and we have a gas of particles, and with the potential energy is just the pair, or any two pairs interact. We saw, and we have repulsion. We understand that the equilibrium position for each particle is NA. And we said that let's look at NA plus YN. And we get the following equation. We said then that let's consider the motion, let's consider the type of oscillations in which Yn can be looked at as a continuous function. Namely, we will approach to this in several different ways. when it is possible to replace the discrete by continuous. I will give you first mathematical example. You see, I want you to understand this transition from discrete to continuous. It permeates modern physics, and this derivation for the special equation of slow varying motion is typical not only here. I will return to this. What I wanted to say is that practically all equations of physics which we know are approximation to something more fundamental, and I will make it concrete later. But let's return to this example, to this crystal example. We said that it is. Let me give you first a purely mathematical thing. Let's suppose we have a sum. So math example. For example, sum 1 over n square plus some lambda. When we can approximate it, it's of course much easier to calculate the integral than to perform the sum. Under what condition it makes sense? So when the approximation is good, what kind of error we're making? And the advantage, if we can do this, is we simplify the problem, because we, for example, immediately conclude how this integral behaves and so on. We can calculate it. It's a very simple integral. And it's much more complicated to do that. So, yeah, go ahead, please.
Large number of n.
Large what?
N.
But I sum over n. How do I know? So I have sum from minus infinity to plus infinity. So how I decide which n are important? That should make it easier. So what do we have this parameter lambda? When you think about the integral, what kind of you tried a reasonable question. What kind of n are really important? Go ahead, please.
We need to know if lambda is very positive, because if
yeah, let lambda be positive. Yeah.
If you're worried about the terms where n squared plus lambda is small.
Say it again.
You're worried about the terms where the denominator is small.
Well, yeah. I don't get you. So finish the sentence.
Around n equals 0 might be where you might have the most error.
Yeah. If we have n equals 0, you think that the sum will be dominated by n equals small n. That's. And what about this integral? Where it sits, where it gets the most of its value?
Same place, but you make
Same place, which is?
around n equals 0.
Oh, well, let's estimate. Okay, let's estimate. Actually, I think it's different than that. Indeed, let's take n equals 0 here. The contribution to the sum, let's call it sigma. Sigma will be 1 over lambda plus 1 over lambda plus 1, 2 over lambda plus 1 plus 2 lambda plus 4, etc. This is the sum, yes? Okay. Now, what you said depends now on the value of lambda. What you said would be correct if lambda is very small. Okay? Indeed, if lambda is very small, it's obvious that this term dominates. Now, if lambda is very small, we certainly get a contradiction if we try small lambda. If we try the whole thing here, the integral, how it depends on lambda, by the way, that's kind of simple. You don't have to calculate it. What?
So with 1 over root lambda?
1 over?
1 over root lambda times what?
That's what you meant, yeah?
Yeah.
Square root of lambda, yeah, sure. Some constant, which is pi, indeed. But I don't want to calculate this integral. What I want to say is that you can always rescale n scales like square root of lambda, so you have square root of lambda on the top and lambda in the bottom. So as a result, you get 1 divided by square root of lambda. It's just a convenient way to quickly get the answer. Actually, you should always develop some set of tools which allow you to get the answer. Some trivial thing, they shouldn't delay you. They should get the answer as quickly as possible. If you do it slowly, you can proceed just as you can't ride a bicycle too slow. Some people can, though. All right, so it seems to be completely different things, this sum and this integral. So for small lambda, this approximation is definitely bad. Now, when it is good? Well, it is good when lambda is very large. And you can see this very simply. As we said last time, we can actually, this is a meaningful approximation if the difference between the two things is much smaller than yn, which is to say that y changes slowly. We just quantify the notion of slowness here. When you jump to the next site, the change is tiny. Okay, so let's see. And under this condition, this is a good approximation. So let's look at this sum. We have lambda plus n square and it should be much smaller than which is indeed the case because if so. I'm sorry. You see, you can always replace sum by the integrals when the characteristic value of n in the sum is large. And characteristic value of n, how we find it that it is large. If lambda is large, you see that all of them basically, for example, if it's basically the same contribution. If lambda is 1,000, then you add 1, you add 4, you add 9, and so on, until you reach this 1000. It's nothing. Nothing changes. And so you really can replace, in this case, y by continuous function. You can calculate, actually you can do it, there are simple tricks which, there's the so-called the Poisson summation formula, which gives you the exact formula in terms of integral plus correction plus correction plus correction, and the corrections are inverse powers of lambda. Actually, here it will be exponentially small correction to at large lambda. But the leading term, and it's only the leading term which interests us here, is simply the integral. So you can say that the function sigma of lambda tends, as lambda goes to infinity, to pi divided by square root of lambda. So that's just to... all right, now returning to physics. We use this to write down we rewrote the Lagrange function as yn dot square as an integral over dn, dy dn, dy dt square minus dy dn square. And the action, maybe I should write the action, integral dt and dn, and this is the action. Now let's derive the equation for the equation of motion. If we take variation of s, you see that we have, well, let's have 1/2 here. We have dy dt delta y dot delta y dot minus y prime delta y prime. Prime means differentiation with respect to n. And what's the equation? What's the equation we get from here, from the condition that this is 0? Tell me the equation of motion which follow from this. Remember what we are supposed to do when we vary. We should integrate by parts so that the variation is proportional to the variation of our variable. We don't want to keep variation delta y dot, we want to get rid of them. Delta y dot, delta y prime. So if you get rid of them, what you get?
The wave equation?
Yes, we get the equation. Indeed, we actually have the equation dt square. That's when we change this differentiation, we moved it to the left. Now there are a few quite interesting features of this equation. And this, by the way, excuse me, I was sloppy here. There was a coefficient c square, and there is a coefficient c square here. And yes, please.
When you wrote the criterion of the difference always smaller than yn,
Yes.
What prevents you from just shifting all the y's by a constant, and then the condition will not be satisfied?
Well, I think that that's a good point, of course. But if we assume here that yn vanish at infinity, otherwise Yeah, that's important. Otherwise, the sum will diverge. But thank you. Yes, that's a proper comment. By the way, I would derive it simply by an alternative derivation is just to say that let's expand maybe for general type of functions as well, let's expand it in a Taylor series, and yn plus 1 minus yn, and that's to avoid the minor bug which you mentioned. Then the question is, you have the Taylor series. You expand it, you consider 1, expand it and dy dn, d2y dn squared, so on, and higher derivatives, yes? Now, we can replace finite difference by derivative if all these terms are small. So more, maybe better criterion would be that y of n must be much smaller than y of n, y prime of n, and so on. And all higher derivatives should be much smaller. In this case, that's simply negligible. We will see it in a moment when we analyze this wave equation. The c square, we derived it last time. It depends on the potential, but what is interesting that this equation, and that's very characteristic for such situations, that this equation, it does depend on the potential, but in a very simple way, only through this constant. So you will, by studying, and that will be basically the situation with general hydrodynamic equation. That's just a special one of special cases of hydrodynamics. We will derive similarly general hydrodynamic equations today. And there are, if we start thinking about molecular motion, which led to this, about potential, there's a good news and bad news. Good news is that we don't have to solve to know precisely the intermolecular potential. All which enters into the equation is this constant. In a more complicated equation, maybe some other constant, and that's it. Bad news about this is precisely the same as good news. Because of that, you are unable to learn anything about intermolecular interaction. You see, if you are asking, suppose I will be doing this, studying these motions, can I say something about this? And then all you can say is this relation. So, and this refers practically to all equations in physics. If you think of Maxwell equations, for example, same story. It's just an approximation to some complicated nonlinear equations, and by studying just Maxwell equations, we cannot really go to beyond a certain point, beyond a certain precision. I will be talking about it more. It's a fascinating feature of modern physics, which actually the standard model of elementary particles, it has the same origin as this thing. And it's just a large, slowly varying approximation, or low energy approximation, sometimes it's called. So this phenomenon is everywhere, and we will study it in this most trivial imaginable case. So we have this equation, and let's talk about it a little bit. First surprising feature of this equation, let me write it down once again. The first surprising feature of this equation is that it is Lorenz invariant. When I say Lorenz invariant, what do I really mean? What is Lorenz transformation? Suppose you believe me and that there is Lorenz symmetry. What is as usual when we discuss symmetry many times already, we are saying that the symmetry is just the way to generate new solution from the old solution. So suppose you have a solution of this equation at particular t and n. By the way, dimensionality doesn't matter in this if we could do it for multidimensional lattice. But it's just simpler this way. So what can you say about what do you think will be Lorenz symmetry? So you have to find white Whittle and express it in terms of y, new solution in terms of old solution. Any suggestions? What is, when you have t and n, I shall remind you the Einstein or Lorenz formulas. This I'm sure you have seen many times. Okay, they actually, let me remind you already, we already mentioned this once. These are symmetries just which preserve the propagation of the wave, and to have this invariant, we did this in this form: lambda n minus ct n prime plus ct lambda minus 1 n plus ct. And when you multiply, you see lambda cancels, and so that's another reminder of the Lorenz symmetry. You know it, and we mentioned it, so I will not dwell on it, but I want you to apply it to this particular case. This is, by the way, the same wave equation which you would get from Maxwell theory, propagate when the light is propagating. The equation is precisely the same, and there is the same Lorenz symmetry. So what is y tilde?
Y of t prime and prime.
Yes, you are right. So we say that we simply use this, and it's now how to see that this is indeed invariant. It's very simple also. Well, the claim is, so far I'm not talking about the meaning of this thing. We are going to discuss it in a moment, but I'm talking about pure algebra. The statement is that if you substitute this into this equation, it will be satisfied. To see this, it's very simple, and actually it's good for solution. When you have this equation, you can write it down as d dt. When you have derivatives, you sometimes can work with them as with usual numbers. So c ddn ddt minus c ddn. Now y is equal to 0. Now, if you introduce variable n prime plus n plus ct, let's call it u, n minus ct is, let's call it v, that becomes d2 du dv. And now u is multiplied by lambda, v is multiplied by lambda minus 1, so you get immediately this answer. As you see, the algebra is very simple. So we have, quite unexpectedly, we started with non-relativistic case, and we quite unexpectedly get Lorenz symmetry. And moreover, what is even more puzzling is that not only we got Lorenz symmetry, but we did not get Galilean symmetry. We started with the Lagrangian, which was Galilean invariant. But now let's check if we have Galilean symmetry. So we have the equation. I shall write it for the third time. Now, what would be the Galilean symmetry and how to check this? So what is y tilde for Galilean?
T comma n plus bt.
Yes. Well, if you like. Okay. Then let's check it. dy dt is dy dt plus v dy dn. As a result, you see that dy dt square minus will be equal to so we get different equation. There is no Galilean symmetry here in this equation, and moreover, it could be understood that there's an interesting story told by Einstein himself in his autobiography, that how he came to his first ideas about special relativity. He said that I was thinking, well, he read some popular science book written by an astronomer whose name was Flammarion. I actually read these books. They're not bad. And Flammarion, he introduced his hero, the guy whose name was Lumen, could move faster than light. And then he moved faster than light. He saw things in the opposite order, happening in the opposite order. That was in the book published by the end of 19th century. Now, Einstein, when he was 16 years old, thought of the following experiment. Let's suppose that you have an electromagnetic wave, and you run precisely with the speed of light, near magnetic wave. Then you will see, what will you see? Huh? The standing wave, of course. But Maxwell equation, this is a simplified version of Maxwell equation, they don't have a solution for the standing wave. Standing wave means that this is 0, and then there is no way to have any oscillations. So something must be. The conclusion was that Galilean transformation, Einstein didn't formulate it in this way at the age of 16, but said something like that later, that Galilean transformation are incompatible with the Maxwell equations. And we see it explicitly here, that the equation changes. All right, but that's, so far it was all formal. And yeah, go ahead. Oh, no? All right. But now we have to understand what's happening. We started with something which had Galilean symmetry. We ended up with something which does not have Galilean symmetry. There is also another thing to be understood. Let's look at a very convenient way to treat such equations, especially in higher dimensions. I think it should be obvious to you that if we do the same thing on, say, 2 or 3-dimensional lattice, consider them, it's just the Laplacian which you put here. Nothing changes basically. So the convenient way which we have to think of is to look for the solution in the Fourier form. Namely, let's take integral. Let's look for a particular solution in the form some, let's say, a of t and k e to the ikn. And let's take real part of it, or imagine it. It doesn't matter. So in other words, it's very. We consider a special type of solutions with particular wave vector k, and what will happen? You will see in a moment why it is so convenient. What will be the equation for A, for the amplitude A? You have to plug it into this equation. So it should be seen without any calculation. Well, there are two terms here. What will give you the first term? It's the question is quite trivial, actually. It's not anything difficult here.
Just a double dot.
A double dot. A double dot eta kn. A real part understood. Now the second term.
K squared, C squared.
Yes. So finally you get A of k and t double dot plus c square k square. When you differentiate ddn, any function of ddn will be simply multiplication by k. Now, what it describes?
An exponential with frequency ck.
That's right, yes. But what kind? You see, it's exactly the equation for a single harmonic oscillator with a frequency omega equal to ck. So the system is reduced to harmonic oscillators. Now, Now it's, since the equation is linear, it is clear that any superposition of such thing is also a solution. And it's known that any function of n you can actually write down as e to the ikn f dual of k. That's the Fourier decomposition. You can always always represent a function as a sum of exponentials. And the reason why it works so well, it's a group theoretic reason. The reason why it is so profitable to expand in Fourier series or Fourier integral is that first of all, the equation is linear, and secondly, it's translation invariant. And I don't have time to go into this in details, but if you are interested, I will explain. The function of the type e to the ikn are the simplest representations of the translation group. So because when you make the group transformation n plus a, they simply multiply by e to the ik. And in general, it's a special trivial case of a general phenomenon. When you are on a sphere, you have rotational symmetry, you expand in spherical function. When you are in a plane, you expand in exponents and so on. But I just wanted to stress that it's not an accident, it's just has a group theoretic origin. The fact that different k satisfy independent equations. That's what was crucial. That if we take some other function, or not exponential of k, you will get mix up of different k's. But the exponentials are when you use what is called representations of the symmetry group, then you get separate equations for each representation. Representations are characterized by this letter k. There is one more thing before I go to this. This equation, which tells us that we reduce the system to the collection of harmonic oscillators. In quantum mechanics, each excitation of harmonic oscillator will correspond to a particle. It can be interpreted as a moving particle in the crystal called the phonon. And they are basically very interesting, actually very strange from the philosophical point of view. You have a crystal composed out of atoms. And that's it. There are no such thing as phonon or something. However, when the crystal oscillates, those sound waves, quantized sound waves, propagate through the crystal, and they behave as if they were an independent particles, although we know that they don't exist. They are just collective motion of the atoms. So it's kind of fascinating for me. That's about reality and imagination. But anyway, so what has happened here? Why the thing to be explained is why we lost Galilean, at which point we lost the Galilean symmetry. And also, we lost not only the Galilean symmetry. Well, let's stick for the moment to Galilean symmetry. I should not overload you. But okay, so At what point when we did this, we lost this symmetry? So remember what we have done. We had some discrete equation, then there are equilibrium solution like that, and then we introduced Weiss, and we found that Galilean symmetry is lost somewhere. Where? I can tell you it's lost at this moment, but you should explain me why. So this is equilibrium positions. What happens to the always we should try to perform the symmetry and see what's happening. So what will happen to this equilibrium position when you perform Galilean transformation? What kind of thing it will correspond to?
So just the particles rotating with constant yield velocity.
Yeah. So in fact, you see, when we choose the particular equilibrium, we already fix the frame of reference. You see, we are not allowed, if we try to move to a different frame of reference by Galilean transformation, we will get new x naught 0, which are an a plus vt. You see, it will be which correspond to this rotation around the thing. So when we our, so to say, ground state, equilibrium state, broke down the Galilean symmetry and broke down, for that matter, the translation symmetry. We have translation by the unit of A, but not originally we had notice this thing. The action was some yk xk dot square plus minus potential v of xk minus xl. We have this thing, and it was symmetric under arbitrary shift alpha. It's not a lattice spacing, but just arbitrary number. And for that matter, we could also add Vt here. That was the symmetry of the original Lagrangian. When we took this equilibrium, we already fixed the frame. So, and we broke down the translation symmetry. And it has a very interesting consequence. Again, the concept of broken symmetry is fundamental in modern physics. And this is the simplest manifestation of broken symmetry, which we have here. And now I'm claiming that because of this broken symmetry, the frequency of this oscillator, I think you will easily trust me that in higher dimensions you will have the same formula with absolute value of k. But notice a particular feature here. Omega tends to 0 as k goes to 0. I claim this is a consequence of broken symmetry. Explain why. Why we, in this simple model, we got frequency which is vanishing for the wave vector or for the infinite wavelength. Wavelength is the inverse of k, of course. So how would you imagine the motion for very small k? Imagine what's happening to those guys when k is small. And it asymptotically approach to some special type of motion. What does it mean? this guy, for generic K, we have a wave, a propagating wave. And what happens to this wave in the limit K to 0?
So for K equals 0, it's just a constant offset.
Yes. So what happened to these guys?
They just rotate.
They rotate as a whole, you see? And this rotation as a whole is just a symmetry transformation. It doesn't require any energy or any frequency. You see? Because of that, because of this symmetry, omega is this. How would you deform the system to find non-zero omega at K equals 0? Well, imagine, that's not a deep question, but imagine that you have external field which breaks down translation symmetry. It's clear now rotation as a whole requires energy. It's only because of the symmetry, of the broken symmetry, we have this phenomenon, massless particles. I'll tell you another example. There are plenty. Physics is permeated by broken symmetries. The simplest example is when you have a piece of iron, magnetized iron, you have a magnet, so spins are oriented along a certain direction, but all direction are, the thing is isotropic, so magnetization can look in any direction. Now you start changing spin, you push one spin and then the wave propagates through the spin. That is called the spin wave, and they play important role in nuclear magnetic resonance, resonance imaging. Now, if you have, if the wavelength tends to infinity, K goes to 0, then this spin wave becomes a simple rotation, and the spectrum of spin wave, or spinons as they are called, they also have this feature that they vanish at K equals 0. It's a more subtle, we will not go into this. Sometimes omega goes like K square, sometimes omega goes like K. It's it depends on, related to time reversal symmetry, but we will not go into this. In ferromagnet, actually, it goes like K square, while in antiferromagnet, the matter in which spins goes up and down, it goes like K. But that's the details. Now, also in nature, we have an example which was very important. You see, we have nucleons, protons, and neutrons, which are rather heavy. And there is also a particle which is related to them, the pi meson, which is about 10 times lighter. And it turns out that it happens because of the broken symmetry. The pi meson would be massless. Massless means this, as you see, this is the spectral equation for photons, for massless particles. And pi meson is almost this massless mode, but not quite because of some symmetry breaking. And there are a lot of spontaneous symmetry breaking related to the Higgs particles. We will not go into this, though. The very important thing in this almost trivial model. You can study this phenomenon. We will see, as a matter of fact, we will see in one of the next lectures that there are cases then you get the mass here. Mass means that omega is non-zero for k equals 0. I remind you the spectrum of energy and frequency in quantum mechanics is the same, and the relativistic formula for a particle is this one. And okay. I could continue indefinitely with this matters. There's a huge, but it is. We should, I think, streamline it a little bit. All right. There is one unanswered question. So the breakdown of Galilei is understood. What is not understood yet? Understood by us, I mean, from the everything is a subject where everything is quite clear. What I was saying, that why we have relativistic symmetry, and the answer is it's maybe disappointing answer. It's just an accident. I will tell you where I can explain this accident. What I mean by that, first of all. You see, what I mean by that is that we obtained this equation by linearizing, by expanding things in Yn. Okay? So we have this Yn, and we expand it up to the first order. And we obtained a second order equation, which is the wave equation. Now, if we expand up to the next order, so we will get some nonlinear term here, then this symmetry will be lost. So it's kind of an accidental symmetry. Why it is there still? You can say something. You can say something like that, that it should be a second order translation invariant differential operator. You can also argue that second order in time should be opposite to the second order in space, and there's only one such differential operator. So it's kind of we assume that Lorenz symmetry is exact, and it doesn't have this origin. But who knows, actually? It was checked to very high accuracy, the Lorenz symmetry, but it could be that at some unthinkable energies it breaks down, or maybe not. We don't know. At least it gives us an example of how it could happen. That, namely, that in some approximation we get Lorenz symmetry, but in the next approximation it's being lost.
Sorry, so what exactly does the second order term look like in that?
Well, you will get, for example, the term when you will get extra terms. One is when you expand further in n, correction to continuous approximation, which will give you d4y dn to the fourth added to this thing, while in time it will be always second derivative, but because it was second derivative in the original equation. The action here gives second derivative. But in space, there will be corrections like that, and there will be nonlinear corrections for, say, like things like that. So there will be plenty of terms when you expand it further. So what I'm doing here, the original system is finite difference system. Now I'm saying it's yn, and I'm saying it's dy dn plus d2y dn square plus etc. And in the leading approximation, we drop this. But in the next approximation, that will appear. And that will break Lorenz symmetry. Okay. So this is an interesting subject, and I enjoy it, but we have to move. And surprisingly, the broken symmetries, they were explicitly realized. People encountered with this type of behavior starting with spin wave in the 1930s and so on. But real understanding that these massless particles, massless modes, have their origin in broken symmetry came with the theory of superconductivity, and then transplanted to the theory of elementary particles. And now it is the central piece of the theory of elementary particles. Okay, now we want to go from this special model to a general description of a fluid. It is again the passing from discrete, from the molecular motion to continuous. We will describe this in a continuous way. The description goes as following. There are two types of description of the fluid. So suppose you have some fluid inside the box. And at the moment zero, let's suppose that some fluid particle is characterized by some coordinate psi. Now, as the fluid moves, this fluid particle will change its position. So I shall probably call it y, call it x. The original position is x, and the position at the moment t is y, which depends on t and x. You see, it's very similar to one of the reasons I spent time on this model is that it's very similar to the general case. And this is called the Lagrangian coordinates, Lagrangian description of a fluid. The motion which we describe by, we need to find the equation for these Lagrangian coordinates. And of course, at time equals 0, it was y was simply equal to x. We will find the equation, and that will be the Lagrangian description of the fluid. Parallel to this, there is the so-called Euler description. So this is Lagrange. And Euler description is different. He simply says, let's take a point x and measure velocity at a given point. And let's write down the equation for this velocity. So, in a sense, the Lagrange description is a co-moving description. You are moving with a fluid. Sometimes it's said that one description is the description from the point of view of a fish, while the other is description from the point of view of a fisherman. I would add to this standard phrase that the fish must be dead. Then it's precise characterization. Now we want to know the equations of motion, and we want to know how these two descriptions coincide. Well, the relation between the two is very simple. We have to relate this velocity. We want velocity at a particular point, so we want to take y of t and x and equate it to what? How? It's a simple question. The relation between Euler and Lagrange description. So what is, we start with Lagrange coordinates, and we want on the right hand side to write something in terms of the velocity at a fixed given point.
Is it v of t of y?
Yes, it is indeed just this. And so if this function is given, then how to find, it answers a rather trivial question. Namely, suppose the velocity field is given. How to find the Lagrange coordinates? The answer is you write down this differential equation, you solve it, and you impose the initial condition that y at 0 and x is equal to x. This is the initial condition for this equation. To specify the solution, of course, of such equations, you need to know the initial conditions. And this is the form. So these two descriptions are equivalent, of course, but sometimes one is more convenient than the other. That's why I'm discussing both of them. Well, now we need the equation. Well, we're running out of time a little bit. We need the equation for the equation of motion, and then there are different type of fluids. We actually need to specify whether the fluid is compressible or not. And the first simplest case is the incompressible fluid. Of course, there are no truly incompressible, at least classical fluids. There are incompressible quantum fluids, like in quantum Hall effect, but not in classical case. But there are simple water is, in many conditions can be considered as incompressible. And I will now tell you what it means in terms of equation, and I will stop there. We'll stop there. So maybe you will tell me, what do you think incompressible means? That if you have some volume, it moves and it remains the same volume. How to formally describe it? My last question for today. What is suppose you have some volume in x coordinate, and so you map x to y. Tell me at least one thing. It's analogous to something which we discussed in ordinary mechanics. What is it? That we have a motion, and it doesn't change the volume. What was it?
Liouville's theorem.
Liouville's theorem, yes. Liouville's theorem is basically that in the phase space, the system is represented by incompressible fluid. Okay, we'll probably leave it for the next time. Let's stop here.